Hello everyone. In the last lecture, we saw I just introduced the concept of synthesis. We also discussed the synthesis flow in summary. That is, what do we do first? First, we load up the library, we read the design, we set the design constraints, and perform the steps of perform the compile. Now, I'll take up each of these steps and expand it and present these steps in much more detail. So the first thing that we should start with is the library. The outline of this lecture is I'll discuss the concept of libraries, how these libraries are designed, a brief view into that, and then how the standard cell cells are selected and combined to form the standard cell library. We'll see the important AC and DC parameters of the standard cell. We'll look at different library views, and then we'll go very deep inside a Liberty file, that is the format of the standard cells, which is written by Synopsys tool. .lib is the short form for Liberty. We'll look at both combination and sequential cells. Then we'll move on to design compiler again, and I'll now introduce how to start design compiler. And then since we study a lot about libraries in this lecture, I'll also touch upon how to set libraries in design compiler. So the concept of digital standard cell libraries is that obviously it is very clear that any logic function can be built using small primitive cells like NAND, NOR, AND, or NOT. So the group of the set of these pre-designed primitive cells is called digital standard cell library. Of course, these are digital. Standard means they are primitive regular standard cells like NAND, NOR, for example. Library is just a term used for a collection of these cells. Now, as I mentioned before, that we are not looking into how these cells are designed. We looked into the design of these cells briefly into unit 1 and unit 2, that how these cells are designed using C#. But the designing and there is a process called characterization is a separate subject altogether. We would during this course we will see how to use them. We assume that these cells are available for us in library format, in the proper format, and we'll see what is inside that and how to use it effectively. Now, digital standard cell library contains logic gates which implement the basic Boolean operations. So now any circuit can be built with minimum basic logic gates. We could say that the smallest number of gates. So the requirement by design compiler is that any standard cell library. So before you embark on doing synthesis, any standard cell library you load should have minimal number of cells, and that minimal number is it should contain OR, AND, inverter, NAND, and NOT. This is the minimum number of cells you should have to implement any logic function. This is the requirement by Synopsys design compiler. But is this number enough to do an effective design? No. So although you could start from a minimal library, but the larger and more comprehensive is the set, the better will be your results. The more flexible you give the tool, more flexibility to choose cells, and therefore the resulting circuit will have better area and better timing. Now, in a typical let's say 90 nanometer or 65 nanometer technology node in industry, typically the standard cell library will have at least 200 cells. Let's see what is contained in those 200 cells. So first, let's see Boolean logic. Let's talk about Boolean logic a bit. Boolean logic is simply a set of functions defined on a binary value variable. Now variable values, depending on what tool we are using, what notation we are using, can be defined in several different ways: 1, 0, true, false, on, off, high, low, VDD, VSS, or depending on the voltage level, 2.5 volt to 0 volt, 2.5 volt is the maximum voltage allowed by the technology. Logic function simply performs their given set of variables in functions, and logic function will perform the transformation. Just refreshing the concept of basic logic gates, inverter and OR. I will not go deep into this. Everybody knows this. So, similarly, you have NAND, NOR, XOR, and XNOR. Now, how do we choose what cells should go into the standard cell library? How is it chosen? So, first rule is that apart from the minimal function set, that is AND or NOT, NAND and NOR, there should be a lot of complex functions also to make sure the design is optimal. For example, you would come across muxes. Now, if we go back and revisit unit 1 and 2, you will see that a mux design is much more area efficient when done with transition gates as compared to normal CMOS logic. Therefore, it is very essential, and mux is a heavily used logical element. So, it is very, very important to have mux. Again, XOR, XNOR, AND or inverse, simple AND ORs, or ANDs. So, it is very useful to have all these different kinds of, I would say, composite functions to have an effective design. Also, let's talk about AND or inverse cell. So, if let's say you want to implement AND or invert function, you would typically need AND or an inverter, right? If your library does not have a corresponding AOI cell. Now, if you go back on paper and try to design a circuit with one AND gate, one OR gate, and an inverter, you would realize that corresponding CMOS circuit of a composite AND or invert is much more smaller. If you see the first example here, the left hand side, this example here, the left hand side, it is the circuit on the left hand side is optimized to represent the circuit on the right hand side, and it is shown that area goes lower. So don't worry too much about how the area numbers came out to be 6 or 4. They are just some numbers here, but it can be shown that using efficient logic design, efficient CMOS designing, the composite circuits have lower area when implemented in CMOS directly as compared to building that circuit from gates. That is why you will notice in the library that there are very lot of different kind of things implementing different functions, and lot of them will have inverter in the end, because the basic CMOS logic is inverted. That is, a 2-input NAND gate is smaller in area compared to a 2-input AND gate, because an AND gate will require one more sort of inverter. You will have a lot of invert functions. You will also have inverted mux and so on. Plus, cells performing same function should be present with multiple inputs. That is, for example, if you have a 2-input NAND gate, you should also have 3-input and 4-input AND gates, ideally. I haven't seen 5-input gates till now in the library because the cell becomes much larger and it loses its effectivity. But there are a lot of cases where 4-input NAND, 4-input AND, 3-input XOR, 3-input OR, 3-input NOR. They are used a lot of times by the tool. So you should give the tool enough flexibility. So we should also have 2-input, 3-input, 4-input type of variants for a particular function. Now, again, in order for cells to be able to drive large number of other cells connected, let's say now you have multiple fan-out here. A cell is driving n number of outputs. Now, a basic cell will not have that much drive strength to drive so many outputs. We will see how that affects timing or transition in later slides. But obviously, a cell with a weak driver at the output will not be able to effectively drive a multiple fan out, a lot of nets, right? So the cell has to be strong. How do we make cells strong? By increasing W by L ratio of the output stage, by having multiples, by having a strong inverter at the output stage. So we should have some cells which can effectively drive high fan out. Now, assuming that, so let's go to the first criteria. You have, let's say, F functions, F cells, which represent different complex functions. You have M variants of each of the cells. M meaning you have 2 input, 3 input, 4 input gates. Thirdly, you have different types of drives of a particular cell. So the total number of cells N would be F into M into K. This is a very gross simplification of the number here, but N is usually 800 to 1500. That is, there are at least 200 cells in a particular mature library. Let's take one example, an AND gate. So there, let's say there are 2 input AND gates. So usually the naming convention would be something like this: AND2, which tells us that the function is AND, the inputs are 2. If you have 3 input, it will be AND 3. If you have 4 input, it will be AND 4. Now there will be at least, there should be at least 2 or 3 variants of AND gates which represent different drive strength. Now drive strength is represented by the suffix. So there will be a cell called AND2x1, which means drive of 1, AND2x2 means drive of 2, double the current drive of AND2x1, AND2x4, that means the drive is now 4 times, as represented in this figure. So you have a NAND gate of 1x drive, and if you try to use this to drive these 4 inverters here, then you will find that the transition here, this transition here is not so good. But if you use a 4x cell as depicted in the right side graphic, if you try to use a 4x cell with a higher drive, it can easily drive 4 inverters, and the transition is very good compared to this case. So this is the use of the high drive cell. So we saw the logic state, standard cell logic state. 0 is represented, is called a low logic level. It can be represented by L or 0. A high logic level, it can be represented by H1. There is one more logic level called Z, which means high impedance state. It is a state where input is disconnected from the output, and output is not driven by it is typically a state of a tri-state inverter, and it is not active. The transitions can be represented by symbols like LH, low to high transition, HL, high to low transition, or X. Now X as a logic level means you do not know what is there on the node. It can be either high, it can be low, but at some point of time you do not know what the state is. This is very useful in synthesis. I'll go on to give you some examples in the next lecture about how X is used. It is very common, very much common in simulation, in the state X. Now let's look at some of the parameters, DC important parameters, DC, and so we'll talk about DC parameters first, related to digital cells. So first very important parameter is the voltage transfer characteristic, as we saw for an inverter. So voltage transfer characteristic simply plots V out, output voltage, against the input voltage, the VDC of an inverter. It tells us what is the function dependence between input and output voltages. The output high voltage nominal value is represented by VOH, N means nominal. It is typically VDD because we want complete swing, so The high logic level is represented by VDD. Output low level voltage nominal is again it will be mostly 0 or negative. It is represented by VOLN. There is something called switching point voltage, which is a 50% mark or where V out is equal to V in. So for a perfectly balanced inverter, V out is equal to V in will happen at VDD by 2 at this place. So it is called switching point voltage. There is something called output high level minimum voltage, so VOH min. Now the two things, output high level minimum voltage and output low level maximum voltage, VOL max and VOH min, are the points on the curve where the slope is -1. So the slope is -1 at this point and at this point. So we take these 2 points, we take the value on the y-axis. So VOH min is the output. So the concept is that what is the output value? What is the voltage value on the output and the minimum value of voltage on the output when the output is high? The nominal value of voltage when the output is high is VDD, as we discussed in the previous slide. VOH min represents the minimum value of the voltage when output is high. Similarly, VOL max gives us the maximum value of voltage when output is low. The minimum value, the nominal value of voltage when the output is low is 0 of VSS. This is the maximum value. Again, we have VIH min and VIL max, input minimum high voltage and input minimum maximum low voltage. So VIH min is the highest input voltage at slope -1. So again at slope -1, so we take VO max and VOL max, and what is the V in value is the VIH min. Again we take the VOH min, and what is the VIL value? It is the VIL max. So it will be clear how these values are used in the next slide. Now all of these values, VOH min, VOL max, VIH min, VIL max, are used to determine the noise margin of a circuit. Noise margin on the higher side, that is when the output is high, is simply VOH min minus VIH min. That is, it tells us that this is the level of disturbance the cell can tolerate and it will not affect the functionality of the cell. Now let's say one inverter is driving another inverter, and the output value of first inverter, let's say there's a case like this where you have let's say one inverter is driving another inverter, and the value at this point at the output of the first inverter has some noise on it. Now the NMH value, that is VOH min minus VIH min, that is the noise margin on the higher side, will determine how much noise can this inverter tolerate. So now let's say the maximum, let's say when output of this inverter is high, that is input is low, and there is a noise on it which causes the input to be slightly greater than 0. Now, if this disturbance is within the tolerance limit, within the noise margin limit, the output of this inverter will not show any disturbance. It will simply ignore the noise. But if the noise is above that threshold, it will cause disturbance at the output. Output will go from high to low for some amount of time, which is determined by the amount of noise. So these two things here, NMH and NML, actually determine those thresholds, those noise margins. So NMH is the maximum input noise voltage, which does not change the output state when its value is subtracted from the input high level voltage. I repeat, this is the maximum input noise voltage, which does not affect the output state when its value is subtracted from the input high level voltage. So let's say the input high level voltage is not VDD, it is VDD minus X. So now this X, the maximum value of this X is nothing but NMH. If the disturbance goes beyond this maximum value, it will affect. If the disturbance remains within this value, the disturbance will be ignored. Similarly, NML, the noise margin on the low side is VIL max minus VOL max. The maximum input noise voltage, this does not change the output state when added to the input low voltage. So on the higher side, any noise which causes the voltage to drop down from VDD is a noise. It might cause disturbance. On the lower side, any noise which causes the VSS, that is zero value, to be increased, and if it does not increase beyond NML, we are fine. All these values, VOH max, VIM, VIH min, VIL max, and so on, noise margin, in fact, they do not matter for synthesis. Why? Because synthesis is not, the process does not take into account noise anywhere. Noise is purely an effect that comes after physical design is done, after place and route is done. We see that noise is part of static timing analysis nowadays in deep submachine technology. In fact, till about 90 nanometers, if I remember correctly, we did not do any noise analysis. We assumed the VDD levels were pretty high, 1.0, 1.5 volts, 1.2 volts, and the noise was not a big concern. So the noise analysis was not part of our implementation. But now it is a very important part of our implementation because the technology has been changing. We pass so many gates in a certain area. So there is the noise is a real factor, big danger now. But still, as far as synthesis is concerned, we do not need to worry about these values. They will come when we start the subject of static timing analysis. So it is only an effect after place and route is done, not before. So synthesis does not take into account any noise leakage. Static leakage, we look at another parameter, static leakage current. When the output is at high stage, you could say when the output is at high or low. So any gate will just because of whenever the transistor is off, it does not necessarily mean the current is zero. There is some leakage current. As the technology is shrinking, this leakage current is becoming more and more significant. This is why even when your most of the devices are off, they still consume some power. So, but again, this value I leakage is not used in synthesis. Then leakage power consumption at the output. Since the current is I leak, the power is VDD into I leak. So the power consumed in the output is high. The leakage is when I say that it's not part of synthesis. There is in fact one case where leakage comes into play. Is there are different kind of cells available in the library usually. So let's say a library typically a deep submicron library from let's say 65 nanometer onwards typically have 2 or 3 flavors of cell. One of the these flavors are based on the threshold voltage of the device. So you could have a high VT cell, a low VT cell, and a standard VT cell. So if we go back to the standard cell selection, content selection, apart from these 3 F, M, and K, you have one more factor which is the threshold voltage of the cell. So a cell which has a high threshold voltage will have less leakage current. Go back to unit 1 and 2 and see these slides. We will find the answer there. Why is it? So high VT means low leakage current. A standard VT device means leakage current will be slightly higher than high VT, and there are low VT devices which have highest leakage current, but again the low VT is the fastest. So the cell with a lower threshold voltage is faster but more leakier. So we discussed, right, the power and speed, they also fight with each other. So the speedier the cell, the faster the cell, the more leaky it is. So you have one more factor here, that you should have cells with different functions, with different number of inputs, with different drive strength, and nowadays we also have cells with different VTs. So for example, we took an example of an AND 2 gate. So there will be an AND 2 X1 HVT, AND 2 X1 SVT, AND 2 X1 LVT. So I'm not sure if the library you are using has multi-VT cells. These are called multi-VT cells, and now they are they are used in synthesis. You could choose to do so. What we do, for example, is we choose to do synthesis only with high VT cells. So we ignore standard VT and low VT to make sure our design is, to start with, it has least power, least leakage power. So it is not, it can be used in synthesis, but it is not necessary. So if your library has multi-VT cells, then you could choose to use that in synthesis. Then again you have, we talked about leakage power convention. P leakage is equal to VDD into I leakage. This is just different. There's some typo here. These are just some different values whenever output is low or output is high. Usually we take average of both. Now let's look at AC parameters. So just summarizing the DC parameters. So typically at synthesis stage you will not see any of these values. VTC is not. VTC is used to derive the noise margins, but it is not part of the library, and typically not used in synthesis noise data. So out of these DC parameters, what synthesis uses is, if you want to enable multi-VT synthesis, that is, you want to choose what VT or you want to do some power optimization, then the design compiler will try and select between different VT devices. For faster, for critical paths which you need to be fast, for high frequency paths, high performance paths, it will typically use low VT cells. For all others, it will use typically high VT cells, so that it achieves the balance of power and speed. Now let's look at AC parameters. Now these are very important parameters. These are typically the parameters you would actually see inside the standard cell library file, and which you would use a lot. The first is the rise transition time. The unit is nanoseconds. Symbol is TR. Now rise transition time is the time it takes for a signal to rise from 0 to 1 from 10% of VDD to 90% of VDD. So we say that TR is the time it takes the signal to go from 0.1 VDD to 0.9 VDD. Now the 0.1 and 0.9 is, we call this 1090. It could also be, you could also have a 2080 or a 3070. It's just a convention. It is fixed for a particular, usually it is fixed for a particular library, or a particular technology. Definition: the time it takes for a driving pin to make a transition from k VDD to 1 minus k VDD. Usually k 0.1, as I told, k is 0.1, we call it 1090. If k is 0.2, it is 2080, and so on. But the choice whether it is 2080 or 1090 should be made right at the starting, and it should be common to all the cells. Otherwise, the analysis, the timing calculation, the delay calculation could be wrong. So it is a very important parameter. We'll see how do we use this. Again, correspondingly, there is a fault transition time parameter. The time it takes for a driving pin to make a transition from 1 minus k VDD to k VDD. Propagation delay. Now, transition times are limited to one signal. The propagation delay, by definition, is the delay, is the time taken for input to reach output, to affect the output. For example, in a buffer, the input rises, the output rises. Now we need some reference points on these voltage signals to calculate the time. So the reference point typically is 0.5 VDD. So the time it takes for the output to reach 0.5 VDD from the input reaching 0.5 VDD is called a TP, or propagation delay high, because output is going high. TPL would be when output is going low. So this is the time difference between input signal crossing a 0.5 VDD, and correspondingly the output signal crossing 0.5 VDD when the output signal is changing from low to high. Propagation delay from high to low is similar, just the polarity is different. So whenever the output signal is going to low and crosses 0.5 VDD, from that we subtract the time at which input crosses 0.5 VDD. Now please note, it is not necessarily that input and output will function at the same time. For an inverter, the input will rise but the output will fall. So the time calculation is done in such a manner that whenever input rises to 0.5 VDD, from that point to the point where output falls to 0.5 VDD. So the 0.5 VDD is the middle point. Again, average supply current, this is the power supply current, average value for a particular time t. Usually supply peak current. These two 5 and 6 are not used for specific. There's dynamic power dissipation. This is the average power consumed from the power supply. So it's nothing but IDD average, that is the average current drawn by the device into VDD. I will not go into 8, it's not used. 8, 9, you could read it yourself. 8, 9 is not that useful for synthesis. Again, you have a switching fall power, you could have a switching rise power as well, the energy dissipated. So instead of reading this as switching fall power, well, let's call it switching power. Switching power is the energy dissipated on a transition. So you have so every gate will have some inherent capacitance at the output that we saw. For example, a NAND gate will have a 2-input NAND gate will correspondingly have a 4C at its 4C capacitance, where C represents the capacitance of each transistor. So every gate has some inherent output capacitance, plus we add the load capacitance, whatever the interconnect is it's driving, whatever, plus the input capacitance of the gates it is driving. Any transition on its output will cause some power dissipation on those capacitances. So this switching power represents that. I will have one lecture dedicated to power, so we'll see a lot of switching power there. We'll discuss in detail about different kind of power, what is important for us, what is significant, what is not. And again, there are so till now we saw that these things: rise transition time, fall transition time, propagation delay. These are kind of delays. That is, these are the properties of signals of output. Let's say output is transitioning from, and it takes a certain amount of time. So let's say there's an inverter, the input goes high, output goes low. Now there are two important things here. One is that delay between input changing and output changing, which is represented by propagation delay. Second is the transition time of the output. How good the waveform of output is. For example, if we go back and see this case, in this case the output is taking a lot of time in going from 0 to 1. In this case, the output is taking less time compared to this case. So the transition time and the propagation delay, they both are delays. Transition is nothing but a sort of a delay. Since the worse the waveform, the more time it will take for output to reach to VDD or KVD. Now here we start looking at not the delay part, but the constraint part. That means constraint is the minimum. There is some limitation on signals changing. If the signals do not change within that time, the functionality is not correct. So one of them is clock pulse width. It could be on the higher side or the lower side. It is typically used for clocks and latches and memory. So if the pulse width, let's say pulse width high, is less than a particular value, then the flip flop or the latch will not function correctly. The time interval during which the clock signal is high or low, so that it ensures proper operation of a flip flop or a latch. Now clock pulse width is not a major issue for flip flops. The CMOS clocks are very fast. They can switch very quickly, and they do not have a very strict pulse width requirement. This clock pulse width requirement is very critical for memory, for full custom memory. Now memories are usually very high density circuits, and to write or read into memory location takes a bit of time, and therefore they have stringent requirement on the clock pulse width. Setup time. Setup time is a constraint for sequential elements. The setup time is a minimum time in which the input data to a sequential element must be stable before the active edge of the clock. So this is the minimum amount of time before which, let's say the clock arrives at some time, at time t. Now the minimum amount of time such that the data should change before the clock arriving at t. This minimum amount of time needed is called the setup time requirement. It's a constraint, it's not a delay. Please note, it is not a delay, it is just a constraint. So if the signal changes, let's say the setup time is TSU. So if the clock arrives at t, the data should arrive latest by t minus TSU. If it does not, then the flip-flop operation is not guaranteed. Similarly, we have hold time. Now this is a time, so data should change only after th. Again, a minimum amount of time. So if you notice that, take a clock signal. Now before and after, there are two limits. So the time before, this is the before, it is the setup time, and the time after, it is the hold time. This is the hold time. This is setup and this is hold. So in fact, if you add up TSU and TH, the setup time requirement and the TH time requirement, it tells you that whenever clock changes for a flip-flop, there is a window before the clock and after the clock. The before window is called setup time window, after window is called the hold time window. The data signal should not change in this window. If it changes, the operation of that flip-flop or latch is not guaranteed. Setup time and hold time, you will see a lot of equations on this using the setup time and hold time, but everything starts from this basic definition. Again, so these are constraints: clock, min pulse, setup, hold. They are all constraints. They are not delays. Now we talk about delays of sequential elements. Now in combination element, for an inverter, for example, input being A, output being Z, the delay is the definition of time taken by signal from going from A to Z. For sequential element, it is the clock that affects that transaction. That is, the clock change data. Let's say for flip-flop, it doesn't, output remains stable irrespective of the data stage if the clock is off. Only when there is a proper trigger in clock, the data is affected on the queue. So the timing, the delay is defined from clock. So the clock to output time only for flip-flops or latches. Latch has two types of time: the combination also and sequential also. We are talking about the sequential time. So the clock to output time is TCLTQ. Is the amount of time that takes the output signal to change after clock active edge is applied. So after clock's active edge comes, whenever output changes, this difference is called clock to output time. Now there are two very specific time constraints for flip-flops or latches with asynchronous set or reset. Now a synchronous set or reset is exactly same as data, because data pin is also synchronous. A synchronous set and reset behaves exactly same as data. So flip-flop is a synchronous set or reset. For example, a flip-flop has the data pin and a synchronous reset. Synchronous reset will have its own setup and hold time constraints, very similar to data pin. But in the case of asynchronous, the situation becomes different. Now the functionality for a clock is such that whenever asynchronous reset becomes active, data becomes 0, or whenever asynchronous set becomes active, data becomes 1. Irrespective of what the clock is, irrespective of what the data pin is, irrespective of the state or any other pin, an asynchronous reset going active will cause the output to be 0 straight away. Obviously there will be some delay, but when the important thing is when the reset is deasserted. So when the reset is deasserted, the next clock edge, let's go to the next sentence. The next clock edge that comes will affect the output because the reset is deasserted. Now there is a minimum time between reset getting deasserted and the next active clock edge that should be met. This timing constraint is called recovery time. So this minimum time in which set or reset must be held stable after being deasserted before next active edge of the clock occurs. So after these edges get deasserted, the minimum amount of time after which the active edge clock can come is the recovery time. So recovery time, if you notice, is just like setup. It is that the reset is deasserted first, then the clock edge arrives. It is very similar to setup. Data gets set up first, then the clock edge arrives. Similarly, corresponding to hold, you have a removal. Again, the deassertion is important. For timing point of view, assertion is not. The minimum amount of time in which the asynchronous set or reset pin to a flip flop or a latch must remain enabled after the active edge of the clock has occurred. So after the active edge has occurred, the minimum amount of time during which this should remain deasserted is called T removal. It is just like hold. So setup is equivalent to recovery, removal is equivalent to hold. So a flip flop, so a combination circuit is pretty simple. An AND gate is pretty simple. It just has, let's say, 2-input AND gate, A, B, output being Z. There are only two parameters here of importance, that is timing parameters. The delay from A to Z and the delay from B to Z. That is it. But a flip flop, on the other hand, has the propagation delay from clock to Q, the setup and hold time for D. If the reset is asynchronous, recovery and removal for reset. So it has somewhat more. It has, so apart from propagation delay, the difference between combination and sequential from timing point of view is that sequential elements have timing constraints. It has timing checks built into it. So we have to make sure that our design, after being laid out properly, after the placement out is done, it meets these timing constraints for all the sequential elements in the design. And this is what static timing analysis is all about. It's a big subject again that will come further. Now there are, apart from the regular propagation delays, output going high, output going low, there are some typical propagation delays for tri-state inverters. Output going from high to Z, from low to Z, from Z to high, from Z to low. This is very typical for tri-state. This is not used for any other type of circuit because only a tri-state inverter or a tri-state buffer has a Z state. So it is very similar to regular propagation time. Now apart from the timing constraint, the propagation delay, we also have something called the inherent circuit design parameters. For example, there is input pin capacitance. So it is the load, and the type of it should be defined through the input pin. The input pin capacitance represents, for example, for an AND gate, or let's say an inverter, you are driving an inverter. What is the capacitance of that inverter? Inverter input pin. As you know that in the CMOS circuits, the input is usually connected to gate. Now that gate has some capacitance, so this is the capacitance we are talking about. Now, input pin capacitance is the property of the circuit, is the property of the design. Similarly, there is output pin capacitance, there is the capacitance of output. These are the properties like propagation delay. Then there is also a constraint that is something called maximum capacitance. This is the maximum capacitance you define. It is defined as the maximum capacitance a gate output can carry. Why maximum? Why not? Why this is there a limited number? We'll come to that. Why maximum capacitance is important. It is very important feature. So now let's see. Let's talk about operating conditions. Now there are three levels of operating condition: process, temperature, and operating. Okay, here it's frequency is given. Let's the process is not given. There is one more thing called frequency. Okay, let's talk about. Okay, the process is not mentioned here, but let me mention the process also. So the process can be, we have also discussed this earlier. A process can be slow or fast, or usually process is represented by a 2-alphabet code. The first represents the state of the NMOS, the second tells us about the PMOS. So a slow process, a slow process, for example, SS tells us that PMOS is also slow and NMOS is also slow. The process, the term actually represents the variation that happens in manufacturing. When a chip is manufactured, there are a number of chips on a particular wafer, and all the chips do not function at similar speeds, because even a slight tweak in manufacturing parameters, even a slight difference going from center to the edge, will cause the CMOS the transistors to be fast or slow. So one thing is process. Second thing is power supply. That is, so typically you create your chip, you will create the design to get certain VDD. For example, it's 1.2 volts supply. But the power supply, it might happen that power supply gives the voltage, which is there is a voltage drop from the power supply. The power supply will go through certain before reaching your design, or before reaching the cell in your design, in particular cell, it goes through a number of meshes. It goes through pads. It goes through the connecting wires. So there will be a power supply drop. There will be an IR drop. So typically the voltage that you get at your design VDD is slightly lower than the VDD applied outside. There is an operating temperature. Now, if the chip is being operated in hot environment, the temperature will be more for that particular chip. If it is sitting in a cold area, then the temperature will be lower. So this will also affect the speed of operation. And then operating frequency is the design spec again. Now, the standard cell library, usually in most of the cases, for the sake of discussion of the course, let's say that the standard cell library, now a cell, a CMOS inverter for example, if it is manufactured in slow process, would be slower compared to the fast process. And if it gets a power supply which is lower than VDD, it will again go slower. Now let's say it gets an operating temperature of 125, it will still become slower, because rising temperature means more delay. So what we define is, we define corners or operating conditions, and we try to capture the full limit of variation. That means we'll have libraries, so a standard cell library, the 1.2 volt process, the 1.2 volt technology for example, let's choose 90 nanometer, and by that, let's say that 90 nanometer design will work on 1.2 volt. You are designing a chip of 1.2 volt. Now we need to make sure that the chip works below 1.2 volts, because most of the cells in the design will not be getting 1.2 volts because of the IR drop. So we define that, okay, the chip should work at -10%. plus it should work for a slow process. Also, it should work at higher temperatures. So now we have three things: P, V, and T. We choose P to be slow. We choose P to be slow. We choose voltage to be minus 10%. So 1.2 minus 10% of 1.2 is 0.7 or whatever. We can choose anything lower than 10% also, but typically it's 10%. So 1.2 volt, the 10% means 0.12. You subtract 0.12 from 1.2, or it becomes 1.28. You could choose also lower than that. It depends on the type of chip, the type of market we are targeting. So usually it's minus 10%. So we choose a lower voltage, we choose a slow process, we choose a higher temperature, and now we get one standard cell library on that. So for example, for this particular application, we have one standard cell library which is 1.0 volts, 1.08 volts at 125 degree temperature and at slow process. On the other hand, we will choose a standard cell library. Now there will be a standard cell library which will be fast for all the cases. It will be at minus 40 degree. It will be at a voltage 10% higher than VDD. So 1.2 plus 10% of 1.2 becomes 1.32. And the process it chooses is fast. So both PMOS and NMOS will be fast. So we choose two ends of the spectrum and verify that our design works for all values in between. Now please note, synthesis will not do this. A tool like prime time, which is for static timing analysis, makes sure the process of static timing analysis makes sure that your design works on all operating conditions which are defined by the process, by your application. Now how do we take care of this in synthesis? Now, in synthesis, we always choose a library which is on the slower side, because synthesis is the output of synthesis is a netlist which is optimized for speed. So we need to make sure that our design, even when the NMOS CMOS are slow, even when the voltage is not VDD, it is 10% less than VDD, even when the temperature is high, 125 C, our design should meet the timing requirement. Our design, for example, if our operating frequency is 300, our design should meet 300 at slow, lower voltage and high temperature. So for synthesis, so when you go on and see your library, you will see that every standard cell library, there will be multiple corners. The file, so there will be, let's say you have 90 nanometer generic library. There will be a 90 nanometer generic library at slow 125 C and 1.08 volt. There will be a library file at fast minus 40 C and 1.32 volt. There will be a typical library at 1.2 volt, 25 C and typical NMOS and PMOS. Out of all the flavors available to you, out of all the operating conditions available to you, choose whatever is the slowest and do synthesis on that. The summary is that synthesis is always done at the slowest library. SS, low voltage, high temperature. This is the key. Rest all operating conditions are used in timing analysis. We will see a lot more of that in Unit 4 or Unit 5. Now, the library data, that is the standard cells, usually comes from some sort of vendor. It can be external, it could be internal. For example, the fabrication lab TSMC itself gives standard cell libraries which are qualified on its own fabrication process. So we could that is an external vendor. Many companies have internal teams that develop standard cells for a particular foundry. Now, what is delivered? What do you get? So we see here that so complete design of library is a set of files which are delivered to customer or user. User will be us in this case at next level. This set of data is called deliverables. There are two types of deliverables: views, and views or files, These are needed by design flow of processes in which the cells are to be used. So the views are actually the files which are used by the EDA tools to do the job. Second is documentation reports. Obviously, we would need some kind of documentation to we will need the data sheets to make intelligent noise, right? This is not directly used by tools, this is a human readable format. The views here might not be readable by humans, might be binary form, written by the EDA tool. This figure here tells the different types of deliverables which are there. So a cell library comprises of cell logic models containing cell functionality, pins, area, timing, power. This is used for, this is the one which is used for physics. So this thing here is very important. It is used for physics. This is called usually a .lib, .lib. So the LIB is a short form for liberty. Liberty is a format in which this data is represented. We will see detail into that. So it contains, what does the liberty.lib contain? It contains logic. It contains for each of these standard cells. It will tell what the functionality is. It will contain the pin capacitances for all the pins, inputs and outputs. It will contain the timing information. What is the delay from A to Z, for example. It will, for sequential cell, it will contain the constraints also. It will contain the area of the cell. So it will contain all the information that is needed by the Synopsys design compiler or the synthesis tool. Second level comes cell physical model. Now please note that design compiler, the synthesis tool, is actually not worried about the physical model of a cell. It just needs to know the area. It is not placing the cell. It just needs area to optimize area, obviously. It does not need any other area information. It doesn't need the coordinates. It doesn't need the pin location, whatever is needed by the physical design tool. So this thing here, the physical model, is used by the physical design tool, used for physical synthesis, operation value. Again, there will be layout of the cell. So cell layout, cell schematic, how the transistors are connected together. This is again used by the backend tools. Used to so the layout tools will use the layout and build different layers, different polygons. From this comes the GDS. It goes to the foundry for manufacturing. Lastly, you need behavioral deadlock models and transistor level models, spice models. This is used to simulate the design at different levels. So deadlock model is used for function simulation to verify that the design meets the function specification. Many people also do spice on some part of the netlist to make sure that the electrical parameters are good, the waveforms are looking fine. Usually spice is done on a smaller level. People will not do spice at a full chip level because it is very time consuming, it is very CPU intensive. So spice is usually done for, mostly it is done for very specific clock generation blocks. For analog, it is definitely spice is the way to go. So a standard cell will have a .lib model, a Verilog model, a layout model, and an abstract model which tells what is the cell size and pin location. Where are they used? So in standard cells, cell description coding specification is obviously used. In logic synthesis, as I mentioned, this part is used, the first part is used. Logic synthesis uses this. Once we are done with logic synthesis, timing, we check timing. If timing is okay, we go to physical synthesis, place and route. Place and route will use this physical model. That's the layout data. It might also use, you could also do spice here. Now again, we verify if the timing is okay. If yes, our design is finished. And there are two different levels of timing check here. 1 and 2. Now 1 is called pre-layout, since obviously it is before physical synthesis. 2 is called post layout. There are a lot of differences between a pre-layout timing check and a post layout timing check. We'll see a lot more detail in unit 5 about the pre-layout and post layout timing check. But the thing to note here is that synthesis is a pre-layout process. The output of synthesis is a netlist which will go to layout. So we will concentrate in this unit. We will concentrate on timing check at pre-layout level and the process of synthesis. We will concentrate on these two. So we talked about deliverables. The logic libraries have timing, power. Let's see the following slide. Now the cell logic model level. It contains. I'm talking about dotlet here. It contains cell name, pin direction, functionality, timing, power, or any other parameter needed by the EDA tool. For example, capacitances. But the process of generating the cell logic model is called characterization. So characterization means that we'll see. I'll mention the characterization will come later also. It means that for a, let's say I'm designing an AND gate, inputs A, B, output Z. Now I need to find out what is the delay from A to Z. How do I do that? I apply some input waveform at A. I observe the value at Z. Let's say keeping B constant. Let's say keep B at 1 for an AND gate. So anything on A will be reflected on Z. But how do I choose the transition at A? What value do I choose? So this process is called characterization, where a range of values is applied on you, and a range of waveforms will be observed at Z. And then we will calculate the transition at Z, we will calculate the delay at Z, and so on. And we will put all this data in the cell logic model, in the liberty file, in the dotlet file. So the characterization goal is that it computes cell parameter, that is delay, output current, or you could say that output waveform is a current waveform or voltage waveform, depending on the input variables, which is output load, input slew means transition, which slew is transition. So typically the characterization is performed for various combinations of operating conditions. So obviously you have one liberty file each for different operating conditions. So we will first fix process, we will fix voltage, we will fix temperature, we will fix PVD. Then we will vary two things. For example, we will vary input slew, input transition, and output load. And now, for let's say we have 5 values of input slew and 5 values of output load. So for a particular PVD, we will have 5 cross 5, 25 output waveforms for each corner, for each cell, and for each combination of input and output. So this produces a different set of graphs, different set of waveforms at different processes, at different input slew, at different output cap. So if you see, X here is output cap, Y here is input slew, and now we put all this data. We put all this data. We choose this number of points here. We calculate the value. We put all this data in the liberty file. We dotlet file. How do we do? What does liberty file look like? We'll see. But just try and appreciate here. Just try and notice here is that how much data is generated. For a simple inverter, let's say there are even only three operating conditions. For 3 operating conditions, for a simple inverter, from input to output, from A to Z, choose 5 and 5, 5 points for input slew, 5 points for output capacitances. You have 25 values of delay and transition. Expand this. Now there are hundreds of cells. Yeah, so there will be thousands, millions of timing arcs in a liberty file. So this characterization is not a small job. That's why you have dedicated teams doing characterization for all these standard cells, and this characterization is done at spice level. Makes sense? You need maximum accuracy. One more view is called the AFRAM view, which is the abstract view of the cell. So abstract view, as the name suggests, it contains the minimal data which is needed for placement and routing. So let's say, for example, you have a layout view here of a cell. I'll leave this as an exercise to find out what cell is this. Now, for this, what is needed typically for layout, for using this, you don't need the internal information. So only the external, the pins, the metal layers that talk to the external world are kept, and rest all is discarded. So you have VDD, GND, which are the power pins, obviously they connect to power rails. And since this cell, when it is used, A and B are connected, Y is connected. We don't need to know what happens internally. So these are preserved. A, B, and Y are preserved. Rest all is discarded. But so this is abstract view. It is used for layout, for placement and routing. But when the data goes to foundry, you replace this abstract view by a layout. Why is this done? The lesser the information a view has, usually the faster would be the EDA tool processing. If the EDA tool is given hundreds of parameters and it needs just 20, I mean, why give it 100? Give it less so that the tool is faster in reading the files and interpreting the data. Now, there's something called naming convention. It's a global naming convention. When you go to the industry, you will find that everybody is using these naming conventions to make the job easy. So .lib is the short form for Liberty. It's a technology library source file, standard cell source file. plib is physical library source file. Flib is symbol library source file. DB is nothing but a lib which is compiled. It is a binary format. It is not readable by us. It is compiled by Synopsys tool, and Synopsys tool read to. PD. So DB is, wherever you see DB, is usually the compiled binary format of the corresponding text format. .v is the Verilog simulation library. Verilog simulation. Now we'll see this in lot more detail. We'll see an example of this. So as I mentioned that a lib is a human readable format. It is converted to DB by Synopsys tool, and Synopsys tool is used with DB. So before a .lib can be used, it must be compiled. So you can use, in fact, you can use the same design compiler program for doing this. It's a very simple command. You read the lib, you read the library file, and you write the lib. So the input is stcadence.lib, output is stcadence.db. So it's a very simple process. Most of the times, when you go to the library, whenever a library is stored, you will see that every library file has a lib and a db already there. If not, then you can use these commands to write the DB off. It's not a big job. Now let's look at example data sheet of a particular cell, an AND tool. This is an AND gate. So usually a data sheet will have a logic symbol which tells you what the gate does. It gives you the truth table where you have values of inputs and what is the value of output for a particular case. It has a naming convention. So this is an AN. So it tells us that there's an AN2 cell and there's a high driver cell also, AN2T. The 2-input NAND gate. It also gives you the number of gates and IOs used by cell. The IOs is 0. It does not use any power, obviously. How many gates it uses. So input. An AND gate will typically use a NAND plus inverter, so it uses 2 gates. It gives the design parameters. It will tell what is the capacitance at input. It will tell how much output load can the cell drive. So for example, AN2 can drive 25 units of load. AN2P, is supposedly higher drive, can drive 57. It also tells you what are the delays from A, B to Z for both of these cells in nanoseconds. It gives you the resistance also, time it takes So there are four things here: intrinsic rise, rise resistance, intrinsic fall, fall resistance. So we'll see how these values are represented in the dotlet file and how are they used. This is a typical data sheet for a particular file. Let's look at one by law. It's very simple. I'm assuming most of you are familiar with the law. So an AND2 gate will have a module definition, inputs, output. The output is declared as register. Whenever any of the input changes, the output gets A and B. There's one more way of doing this. You could replace always by an assign statement. Assign F is equal to A and B. In that case, there's no need to define. The F will be not a register but a wire. So you could write the different description in a number of things, number of different ways. Now let's look into detail into a library, into a dotlet file, which is read by a design compiler. Cross synthesis. So the library definition file, any example.lib, is broken into two sections. One is the header, which defines the most common values for a lot of parameters, and then an individual cell section. A cell's definition will define the attributes about the cell, such as the name, area, functionality, time, power, etc. Let's start with it. So this is a library header. The library always starts with a library syntax, which is the name of the library. Technology tells us what type of delay model is the library. So the technology is CMOS. The delay model tells us what type of delay model we are talking about. I'll go deep into this again in following slides. Then these values here, these default values here, define the defaults for input pin capacitance, in-out pin capacitance. In-out pin is a pin which has both of input and output, is configurable. It defines the output pin capacitance. Now these are default values. That means if any particular cell, for example, I define a cell but I do not define the input cap. In that case, if the input cap of the cell is not defined, it will take the default value. So it is a good practice to have these. Since if you miss any particular attribute, then that will not be zero. It is not zero here. So if you miss out the input cap definition for an inverter, it will take some value which is defined in the default. Then it defines the units, timing unit, resistance unit, voltage unit, current unit, capacity. So the units are defined here. Then the nominal operating condition is defined. So nominal process 1, nominal temperature 25, nominal voltage 5. Obviously voltage will have the unit of volts, temperature will have the unit of C. Now the process thing here tells us that nominal process is 1, and I'll come to this. Now further in the header we can define, so now we can also define different operating conditions. We say that, okay, we define one worst case condition, WC. The process is now 1.5, temperature is increased, it is 70, voltage is decreased. So the worst case corner, as we said, voltage is decreasing, temperature is increasing. The process factor tells us that since the nominal process factor was 1 and the worst case process factor is 1.5, it tells us that all the delays in this library, if the delay was 1 for nominal and you choose the worst case corner, this particular operating condition WCC form, all the delays will get multiplied by 1 by 1. So all the cells will get 50% load for the worst case corner. You could also choose something called the operating condition BC range, which is best case. Forget about tree type right now. I'll come to this in later lecture. Again, for best case, see the temperature goes lower, -40. The voltage goes higher. The process is 0.6. So the process factor tells us that since all the NMOS and PMOS are becoming faster, all the delays relay values in this particular library for a best case corner, for a fast corner will be multiplied by 0.6, or all the delays will be 40%, all the cells will be 40% faster. This particular case was used, this particular type of writing the operating conditions and using the operating conditions was used few years back. It is not in use now. Now what happens? Now this is a very simple model. That is, what we are doing here is we have only one library file now, which has data for nominal. Now what a tool does is that if you say tell the tool, okay, I am choosing WC comma, which is the worst case. What the tool will do, it will use some factors to make the delay slower. If you choose the faster corner, it will make the delays faster using the same process factor. But this is a very simplistic model which does not serve present day nanometer design. So now in present day in the industry, what you have, mostly you do not have this. Instead, you have one file per operating condition. That is, there will be one file for worst case corner, one file for best case corner, and there is not a single worst case corner or best case corner. The things are too much complex now. So let's say, for example, you have two worst case corners and three best case corners. So you will have two worst case corner files, three best case corner files, and if you compare the delays, in each file will have separate delays. And now, let's say you are using, and now you have to read that particular library. So if I want to do synthesis, for example, I will only read the worst case file, the worst case library. And if I am doing timing analysis, I have to make sure that if I am doing a post-layout timing analysis after process out design, I have to make sure that my design works on all the corners defined. That is, I will perform that process 5 times on 2 worst case corners and on 3 best case corners. The things will become very clear in Unit 5. But for now, as an assignment, you go back, check your library file which you have. Probably you will have a 99mm generic file from Synopsys. Check that you have one library file per corner. Now let's look at this was the header, what we looked at. Now let's look at the cell definition. Now let's look at an AND 2 gate. So this is the cells, the starting of the cell. Area is defined here. So please note, this is just the area number which is written there. We are not writing what is X and what is Y. Usually the layout is rectangular, but the synthesis tool, since it's not doing placement, it's not actually placing the cells, it does not need X and Y. It needs simply the area. We define the pins A1, B1, O. We tell the direction. A1 is input, B1 is input, O is output. We write what is the input capacitance, and we also tell what is the function. So only output pin will have the function, obviously. The function tells us that it is A1 into B1. So it's an AND gate. Now design compiler, when it reads this library, it knows that the area of the AND gate is this. It has these inputs, this output, and it knows it's an AND gate by this. It does not know it's an AND gate by the name. It knows that it's an AND gate by this function. The name can be anything. Timing has been removed to simplify this. We will see the timing in the coming slides. We will see an AND gate, 92_4, probably it means that the drive is 4, it's a high drive NAND gate. The area again is 359.1. There are 2 inputs, it's a 2 input NAND gate, so it's a 2_4. Capacitance, again function. So function is A1 into B1, and complement is used, a single quote is used for inversion. Now please note there is no output capacitance here. There is no output capacitance here. Does it mean the output capacitance is 0? No. Look for the value in the header. So if the output capacitance, for example, is missing, the tool will take the output pin cap from here. default value is also 0, so obviously it will be 0. So it's the job of the standard cell designers, of these people who are doing characterization, to make sure that there are no 0 values. If the values are not negligible, they should not be 0. Let's look at a flip flop, a sequential cell. Area is something. Let's look at pins. There's a data pin input, there's a clock pin input, there's a reset pin input. Q is the output. Now how do we tell the function? The function here is defined to be IQ. This IQ is, so this is this construct here. We construct this construct here. FF is specifically for sequential cells recognized by the tools. So we tell that FF is always IQ, IQ. This is the fixed syntax. So we tell that the next state is data. So we tell the tool that it's a sequential cell FF. The output is IQ, which is mapped to Q. IQ is mapped to Q. The next state on IQ is data 1. That is, whenever there is a trigger on clock, so it is clocked on clock 2. Whenever clock comes at clock 2, positive edge clock, it's okay. So there's a single quote here, so it becomes a negative edge. So whenever negative edge comes on clock 2, data 1 goes to IQ, and IQ again is mapped to Q. So you tell the tool that this is a flip flop with data pin being data 1, output 1 being Q. Clear is RST3. It is an asynchronous clear. It tells that the inversion on reset. It is again there's a single quote here. So it's whenever the RST3 goes low, Q is clear. So it becomes 0. Now, before looking at the timing section, let's talk about synopsis timing model. Now, representing the pins, telling the tool, writing the pin direction, calculating the output gap, input gap, telling the function, they are all simple jobs. Why? Because there's only one single value to be compared about. The input cap will be a single value, the output cap will be a single value. But what about timing? Timing is not a single value. Timing depends on how much load are you driving, how much load, how much transmission you are getting at the input, and some other parameters. Right? So representing timing, for representing timing, you need some mathematical model to calculate timing and to write the timing in the dotlet file. So there are I have mentioned 3 models here. Linear delay model. So if you go back to the header here, so this delay model string here defines what is the model. So a generic CMOS tells us that it is a linear delay model. If you see something like table lookup, it means it's a non-linear delay model. If you see piecewise CMOS, it is piecewise linear delay model. Now, the first one, linear delay model, is a very basic model, simple model, and that is why it is not used for present day technology. But we'll go over this. We'll lay some foundation here. This was non-linear delay model, short form we'll call it NLDM, was the most famous choice of models till a couple of years back. Not even couple, 3 or 4 years back. It was the most popular choice of model. In fact, your Synopsys 90 nm generic library will have an LDM. So we look at this in detail. We will, for presently, we ignore these guys. I haven't seen it used. But now, in present technologies, all these 3 are not in use. Although NLDM is still used by some other tools, not by some other design compilers, present day compilers. It might be used for some old tools. This remains most popular, but now it is being replaced by something called CPS, constant current source model. But I will not go into this. For this purpose, for the purpose of this course, studying NLDM should be enough. Now let's look at linear delay model. We again go back to the 2 input AND gate. Now we see few values here. We see intrinsic rise, we see intrinsic fall. This tells us something. This tells us that there is a rise delay on Z. So timing is represented by a timing construct here. So first thing to note here is related pin. Both A and B are mentioned here. That means this timing construct is valid for, is applicable for both delays, A to Z and B to Z. There is some delay when Z rises. Intrinsic rise means that. Intrinsic fall means that there is some delay when Z falls. Now let's see how these values are used. There is a rise resistance also, there is a fall resistance also. These two will also determine something. Let's see how it is used. So in a linear delay model, it involves calculating the the process of delay analysis or the delay calculation involves calculating the delay between input pin of a gate and the input pin of the next gate. Therefore, this timing delay includes the interconnect delay also from the driving pins to the load pins. The linear delay model, it divides the total delay of network into 4 physical components and sums them up to the circuit element. So the total delay is Di plus Ds plus Dc plus D. Di is the intrinsic delay inherent in the gate. It is independent of how it is connected. It is independent of how much fan out is there, what net length it drives. It is simply an intrinsic delay. Again, if you remember, the intrinsic delay is nothing but a function of what is the capacitance at the output. Again, there is something called slope delay. Now, slope delay is the delay effect caused by the transition at the input. If the input is not ideal, it will take some time to transition from kVDD to 1 minus kVDD. So it is the slope delay is caused by that. DC is the connect media delay to an input pin, is the wire delay. DT is a transition delay caused by the loading of the output. Now the fan out will consist of some wire and some gates. DC is the wire delay. DT is the delay caused by the loading of the gates at the output. It will become clear in the figure. So let's take this example where we are interested in calculating the delay for this gate, for this NAND gate. So Di is the intrinsic delay incurred from cell input to cell output from A to C. Ds is the slope delay at input A caused by the transition delay at B. So whatever inverter, let's say inverter is driving B, there will be some transition profile at A, and that will affect the delay. DC is the connect delay from the interconnect from C to D, the interconnect loading. So we are talking about delay from actually A to B. So it will be A to C plus C to D. So it is the connect time is from C to D, the straight transition that takes place here. Again, DT is a transition delay which is caused by the output loading. That is the loading caused by these two inverters here at C. Now, what happens in synthesis? In synthesis, usually, now in synthesis, you will not have information about the interconnect because simply the gates are connected by logical wires, not physical wires. Logical wires do not have any capacitance, they do not have any resistance. So any interconnect delay calculation will purely be an estimate. And how do we estimate that? We will see. But for now, assume that there is some delay with DC, there is a connect delay. And now let's look at the equation here. So now, so D total, so Di would be. So what we could do is, if you do not want to estimate wire delay, it will take wire delay to be 0. It will take the value of intrinsic rise and intrinsic fall. So for the rise, it will take this, plus it will do some calculation with rise resistance, and there is a default slope and default slope fall time and rise time because of the effect of it is 0 in this case, but you can have a positive value here. There is a default fan out load also. So it is So if we do not give all the values to the tool will make some assumption and it will use this equation for linear delay model to calculate the delay. Now let's look into NLDM, non-linear delay model. It's a very interesting concept. Now a linear delay model suffers from some shortcomings. It is not enough. It is not accurate enough to represent present nanometer technology. Even 90 nanometer is not good enough. So it is replaced by non-linear because simply the linear delay model as the name suggests, the delay at the output will vary linearly if the input changes, and it is not the case. It is not a straight line. It does not vary linearly. Now NLDM proposes that the total delay has two major components: the D cell and the DC. The D cell is again the intrinsic delay, typically defined as the 50% input pin voltage to 50% output pin voltage. Now D cell is computed, can be computed in two ways basically. DC in this case is the connect delay. It is either calculated with the wire tree type attribute and selected by our model. We'll see later about this tree type and wire model. But DC here what it tells us is that DC is nothing but an estimate. Based on some input we give, the tool will estimate the interconnect delay. Right? Now, in the absence of D cell component, D transition, which corresponds to the time required at the output pin, is used. We'll see that we will use D cell and D transition interchangeably depending on how the data is provided. It will become clear in the coming slide. Now, as we mentioned in the previous slide, there are two methods of computing D cell. The two methods are that the delay is already provided as a lookup table. So there is a table, it has some entries, and the table represents the delay value itself, complete delay value. So the tool will just do the interpolation. We will see how. Second method is we provide two tables, propagation table and transition table. Directly the delay is not given. The delay is split into two parts. The first part, the propagation, represents the propagation delay. We saw in the, I'll go back quickly to point out two things we use here. So it will have two things. One is the propagation delay, this thing here, and this thing is the transition time. So please note, propagation delay is the time difference between input signal crossing 0.5 VDD and the output signal crossing it 0.5 VDD. Transition time is the time it takes for the output pin to make a transition from KVDD to 1 minus KVDD. Now D cell is broken into two parts, D propagation. So there are two tables, one is the propagation, one is the transition table. Now to conclude both propagation and transition, again it's a lookup table. So the time between two reference signals on the output pin, both of the processes require interpolation. So the typical measurement for D propagation is again 50%. We mentioned this. And thus a D transition value from 10%. So yeah, let's read this. The typical measurement of D propagation is a time from 50% input voltage value until the gate output just begins to switch. For example, okay, yeah. Now, so the output will begin to switch. We say that, for example, we are using a 1090 rotation. So we say that the output is beginning to switch at 10% of VDD. So the D transition value of going from 10 to 50% is added to the D propagation, because the D propagation is calculated from the point of 50%. Now look at the two cases. If the cell delay table, if directly the cell delay table is provided, it becomes very simple. The D total is D cell plus DC. If the D cell is not provided, D total, D cell is nothing but D propagation plus D transition, where the propagation delay is again 50 to 50. And the D transition is the remaining value. So D total becomes D propagation plus D transition plus DC. Let's look at a lookup table. So a non-linear CMOS lookup table can use either a one-dimensional, two-dimensional, or three-dimensional lookup table. Depends on the accuracy we want. Let's look at an example of 2D table. For a 2D table, one axis must be input transition time, and the second axis can be different choices, one of which usually is the total capacitor mode. This is the most famous type of the lookup table. Now, this is a two-dimensional lookup table. The format is like this. We say it's T4, this name can be anything. Variable 1 is a total output net capacitance. We are saying that the output delay and output transition both. Now we are using this method here. We are using propagation and transition method, which is most famous. So we are telling the tool that my output delay depends on two things. One is the output net capacitance, other is the input net transition, which is in fact a physical thing. And for output net capacitance, I have chosen 4 values: 5, 20, 60, and 200 units of capacitance. For input net transition, I have chosen 3 values: 0.01, 0.1, and 2. The units can be anything, but it should be consistent. The data should be consistent. Typical unit for capacitance is femtofarad. Time unit is usually PS or NS, picosecond or nanosecond. So now this lookup table tells me that the characterization has been done on 12 points: 4 on capacitance, 3 on transition. Now this is the value of x-axis and y-axis. What about the actual data values? These are the actual data values. Now delay timing, so data is added to the output pin definition. Obviously the output, the timing and the function is an attribute of the output. So we see here that there is an output pin. This defines the function, and now the timing construct starts. And you have a table here. Now this table here has 12 values: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm not sure this is some typo here. This should be till 12. There should be actually, yeah, these values should not be here. So they are considered there are 12 values, each corresponding to one of these. So for example, add the capacitance of 5 and the transition of 0.01. The output O, the rise time, the cell rise time is 0.74. So this is the direction. Again, add the value at the output net cap of 5 and the transition point 1. The output pin O has a cell rise of 0.75. So this index 1 is always the x-axis, and this is the y-axis. So this is the way in which it is modeled. That is why we call it a non-linear delay model. This is not linear. The more number of points, the more accuracy you have. It's just a curve fitting exercise. The tool down. So now what synthesis or timing analysis tool will do? It will know the output. It will know the capacitance as an output of a gate. The output pin of a gate will have its own capacitance plus the fan out capacitance plus the interconnect capacitance, which might be estimated. And now it knows the input pin capacitance. It knows the input transition by it will propagate the signal. It will know the input function. For that value of input transition, for that value of output load, it will interpolate. The values will not necessarily correspond to these points. They will be somewhere in middle, and the tool will interpolate. What happens if the tool finds that the output cap lies beyond this? Now it will extrapolate, and since everybody would agree that if there is a set of data given and we interpolate, the accuracy when we extrapolate goes lower. Now, what does this value of 200 tell us? This 200 tells us that the standard cell designer chose this to be the maximum value of the capacitance that this cell can drive, obviously. And if the cell is driving more than this, the tool will extrapolate and the results will be inaccurate. So, this 200 defines the maximum capacitance that O can have. This is the concept of maximum capacitance. Or the input transition, the max value here 2.0 defines the input, the maximum transition A1 and B1 may have as an input. So these maximum transitions at inputs and the maximum capacitance at outputs, these limits, these maximum limits are called the design constraints, the design rule constraints. This is the first priority of a synthesis timing analysis tool. You have to make sure that your design meets all the constraints, all the max function and all the max constraints. Only then, only after meeting these constraints, you can be sure that the delay calculation is accurate. So the timing data forms a lookup table. Each grouping of data corresponds to values of index 1 with index 2 to select the value from the group. In this example, there were 4 capacitor load values, 3 input transition values. So there were 4 groups of data with 3 data values per group, or total 12. You could choose to read that in whatever way, but please note that there are 4 groups of data. When we say that there are 4 groups of data, we mean index 1. Index 1 defines how many groups of data. Index 2 defines which value to select from that. So all the 4 things, cell rise, cell fall, rise transition, fall transition, will use the same table. This is the same table with the given indexes. So this template is common to all 4. The values will change, obviously. The designer chose 4 capacitor points, 3 transition points, and at each of these points, the designer calculated the rise delay, the fall delay, the rise transition, the fall transition, and put it in here. So these are the 4 things: cell rise, cell fall, TPHL, and TPHL are propagation delays. Cell rise, cell fall are propagation delays. Rise transition, fall transition are the output transition values for the output signal. The indexes should be chosen to represent the range of values in the design. This point is very important. Do not count on accurate timing results if the algorithm has to extrapolate. We saw the propagation delay for the propagation delay is similar for combination of sequences, only the related pin changes. Let's look at the constraint setup hold time. So we can use either 1-dimensional or 2-dimensional lookup table. Usually 2-dimensional is more famous. Setup time, please note, setup and hold time are between data and the clock pin. So the 2 things important here are the constraint pin transition, which is nothing but data, and the related pin. Related pin is always clock in this case. Index 1 tells us that these are the transition values on data. Index 2 tells us that these are transition values on clock. So a data pin will have related pin as CLK2. Setup falling means that when clock 2 is falling, it's a negative edge trigger clock. When clock 2 is falling, what is the setup time? When setup falling means when clock is falling. Rise constraint means when clock is falling and data is rising, what is the setup time? When clock is falling and data is falling, what is the setup time? So these are the 2 setup. This is the setup timing constraint, setup falling. So each timing construct here will contain one particular type of timing. So this is setup falling timing. It uses this table. It has 9 values. That's total 3 groups. Each group has 3 values corresponding to. The group is represented by index value 1. The data within the group is represented by the index value 2. Now about the index values. Now we can specify index values in a lookup table data and use placeholders. So in this case, the template here, the lookup table template here, and the lookup table template here, they contain the real values of capacitance and formation, for example, which the designer used to characterize. These contain the real characterization values. But what we could also do is we could use dummy values here and fill up the values. So in this example, these are real characterization values, and we are filling the delay values here. The second, there's one more way of doing this is that we use placeholders here and just tell that how many points are there. So these are just dummy values. But when it comes to writing the values here, we specify the actual values of characterization. This lets us in. So for example, now let's say two cells, two AND gates. One is low drive, other is high drive. The higher drive should ideally drive a larger capacitance. If we were using this kind of lookup table, then this value 200 will change for high drive cell. Let's say the value for low drive is 200, for high drive it might be 800. We cannot use the same template, right? So we can use this particular method, use placeholders here, and now when it comes to low drive cell, we could apply the values here and use the same template. For a high drive cell, again we could use the same template and use the value of 800. So there are two ways of doing it. Depending on how the standard cell designer chooses to characterize, we can choose to define values there. But it's important to understand that what are the actual index values. So if you see index values in a cell drive table, that means these are overriding the ones given in this template. That's the important thing. How the index values are chosen? Index values are chosen based on, it is important not to let tool extrapolate. The leftmost value of the transition, it could be the transition time of fastest cell, that is the largest inverter with no load. That could be the best transition time available to you. So you can choose that as a minimum value. The rightmost time could be the transition time of the weakest output, driving the largest expected load. So the designer will choose the value in such a way that this can be the worst transition time he could expect. Similarly, for capacitance, the leftmost could be smallest pin capacitance. You could add some margin to it. The rightmost should be the largest pin capacitance for maximum allowable panel. You don't need to worry about these. You just need to be aware that how these values are used. This one is with the standard cell designer. Lastly is the number of indices. How many number of indices you choose? For let's say for load, how many indices you choose? For transition, how many indices you choose? Obviously, the more the number of indices, the more accuracy in interpreting. But again, how much spice are you willing to do? Each corner, each data value needs one spice analysis. Most of the characterization systems obviously are automated. You cannot do it by hand, and it just depends on how much accuracy do you want versus how much machine time or man hours you can spend on the characterization process. Now, this is all about libraries. We saw how the data is represented inside dotlet, how the combinational cells are represented, how sequential cells are represented. We saw the linear delay model and the non-linear delay model. We tried to understand how the non-linear delay model is represented inside the dotlet. We saw how setup and hold times are modeled. So as an assignment, please go back, open whatever library you have, the 90 nanometer CMOS generate library. Choose one combinational cell, choose one sequential cell for both of these cells. Look at how the data is represented, what is the function given, how the lookup tables are given. Are you able to understand what is the max capacitance value? Look at the header, what is the delay type there, and so on. Just go through this lecture and map it to the library you see. Now the question is, how do we use this library? So the first step in a synthesis process is to finalize the library. Let's say I finalize the synopsis 90 nanometer library. Now how do I use it? So the next few slides are they tell us how do we start the DC shell and how do we load the library. So running DC, invoking DC is very simple. You use DC underscore shell. Obviously, you should have the path set in your environment. You should have some variable set. Obviously, you can take help with the lab guy to do this. You can open it in GUI, but I would recommend starting with the text-based the command line interface. The best practice is that early in the design phase, it is good to decide on the design naming conventions, the design style, directory structures, and revision control systems. Obviously, for big projects, it's very essential. Now there are DC setup files. This is the most the synopsis DC setup file. It is automatically read into DC startup. Whenever DC shell starts, it will load up this file. It will try to find this file in this order. First, it will look in the root, then home, then local. It is best used to customize your work environment. Now, let's say you are, let's say I am in charge of a particular project, and 5 guys under me are doing synthesis. Now, I could write up a synopsis DC setup and use it so that each of those 5 guys, when they start this DC setup, they get the similar environment. So I could set my libraries there. This will make sure that each of those 5 guys is using the same set of libraries. So I could do that by using this .synopsis DC setup file. Example of this synopsis DC setup file is this. It is must to have a hash character in the first line of the file. The variables are set here. We'll see what each of these variables mean. Search path, target library, synthetic. So this is an example where we are setting up library in the DC setup file. You could set a lot of things here. You could set a lot of variables here. You could choose not to set up libraries here. It's up to you. So library setup. This is how we set up the library. We set up the search path. Search path allows the files to be read in without specifying directory path in the command. So this is a set of directories in which the DC will look for library or design file during a link process. We will see more details of this. So, for example, the search path here is given dot. There are three things here. $search path means whatever is in the code, just append to this, just append dot and this to this. So, if you read in any design file or read in any library, it will search in these 3 directories if you do not give the complete path. Target library is the actual standard cell library which you want the tool to use to map your design and optimize your design. Compile process will choose inferred cells from the target library. This is a very important word, inferred. That means if you have written a Verilog RTL code, you are telling the design compiler by the use of target library that use this library, use the standard cells in this library to implement my design. Something called synthetic library is a list of designable components. I told you before, designable is a collection of a lot of things, and a synthetic library is just a collection of, it is nothing but a design list. So you could use priority encoders, arithmetic operators. It even has a microcontroller and so on. It has a lot of cells, lot of pre-fabricated design. Fabricated in the sense logically fabricated. So you will have a lot of ripple adders, you have boost multipliers and so on. So this is the name of the library. So it is set like this. So synthetic library is set like this. DW foundation means the design library. Link library is used during linking, pre and post compile. All the cells in the design must be in one of the link libraries. Inferred cells means whatever design compiler used to implement from the target library. You could have, let's say your design has a PLL. Now PLL is not a cell which design compiler will use to implement anything. PLL is a very specific cell. It generates a clock. So you will instantiate a PLL in your design. So a PLL or a memory will never be part of a target library because design compiler will not use it to implement anything. However, it will be part of a link library because design compiler will use it to link. Design compiler needs to know, let's say, for a memory or a PLL, what are the pins? What are the output functions? How do I connect them? It doesn't need to know exactly what is the functionality of those complex cells like PLL or memory, but it needs to know the pin. So these are called instantiated cells, specific cell instances placed in the RTL. So these will be part of the link library. Link library must always start with a star. This indicates that loaded design should be searched first. All synthetic and target libraries must be included in link library. This is the example here. The link library is target library, obviously, because target library will use, when you synthesize, the corresponding netlist will have cells from the target library. So when you all the cells in target library should be part of the link library. So link library has these designs are loaded from memory, target library, synthetic library. These concepts will be very clear when you start using design compiler. If something is not clear at this point, you could always go to the tool, start using it, and things will become much more clear. There's a command called define design lib. It is a directory where DC places intermediate design files. It will compile the verilog and produce some intermediate design files. Default is the directory from which you are running the DC. If you do not define this, it will dump those files in your present directory. It is very useful to define the design lib to be someplace else, so that you don't have a clutter of data in the present directory. Then set don't use is a command which tells a synopsis that which tells design compiler that some cells from my standard cell library should not be used. It is a very common practice to not use, for example, high drive cells during synthesis. The high drive cells usually people use in very specific cases because they consume a lot of current. So people use the high drive cells mostly for very specific cases, that too after the placing out has been done. So it's a very usual practice to define high drive cells as don't use. So this is the example best practice here. I guess that's it. Yeah. So I'll just summarize what we saw today. We saw in detail. We saw how the standard cell library is made up, what type of cells it contains, the high drive, the multiple drive cells, the multi cells, different functions, different sort of different inputs, number of inputs, for example, 2 input NAND, 3 input NAND, and so on. We saw what are the deliverables standard cell library should have. It should have a verilog, it should have a .lib file, it should have a FRAM or an abstract view, it should have a layout. Different tools will use the different views to implement. We saw inside of a .lib, we saw an example of verilog, a data sheet. We saw how the cells are modeled inside .lib. .lib is the most important file which Synopsys uses for synthesis. So we saw a lot more into that. We saw how the function is represented for combination sequential. We saw two different timing models, linear and non-linear. For non-linear, we saw the lookup table and how the delay and transition numbers are represented there. So it's it would be very useful, very good now to go back, open up the library, and spend some time in conjunction with this lecture. Thank you.